Hi, everyone, and welcome to the NeuroNexus podcast, where we take a deep dive with the researchers using our tools to push the fields of electrophysiology forward. For over 20 years, NeuroNexus has been a leading provider of silicon probes. In response to the evolving needs of the field, we've expanded into data acquisition systems, accessory instrumentation, and cutting-edge software, together supporting rigorous research featured in nearly 5,000 publications. In this show, we break down the science, the setup, and the real-world lab experiences that don't always make it into the publications. Whether you're a longtime NeuroNexus user or just getting started in electrophysiology, you'll find something useful, relatable, and inspiring in every conversation. So let's get into it.
Okay, perfect. But yeah, so definitely super new to the team. I'm learning a lot, getting to meet a lot of the people that are using our products. But yeah, I'm having a really good time. And so what about you? So you're a postdoc in the Buzaki lab.
Yes.
Okay.
I started my postdoc 5 years ago, 6 years ago now. I'm doing extracellular electrophysiology, both in my stats. We do head-fixed recordings, optogenetics, behaving animals. And to be honest, I use all kinds of probes,
Yeah.
so including the NeuroNexus, some of the competitors. Yeah, and the most recent that we used was the synapse probe. And my project mostly focuses now just understanding learning and memory, but
Okay.
some of my projects are also focusing on non-invasive neuromodulation and whether we could improve learning and memory with electrical stimulation.
Neat. So what regions of the brain are you interested in? What are you looking at right now?
So we are recording mostly from hippocampus, but also some cortical areas. So the hippocampus is part of the limbic system, and it's really, we really know at this point that it's responsible for working memory, and it's involved in encoding of recent experiences. And then we typically try to record from some cortical regions so we can understand how this temporary memory storage from hippocampus, the information or recent experiences can be transferred into long-term storage in cortical areas.
Okay. Neat. Now, are you recording from multiple regions simultaneously, like hippocampus and
Yes.
in the cortex? Okay.
Yes.
Tell me a little bit about the prep for that.
So we typically attach each probe to its own microdrive, and then we have one probe targeting the CA1 region of the hippocampus, and then another probe either to retrosplenial cortex, which is part of the default mode network, or another probe into prefrontal cortex, which receives direct input from hippocampus. So we can study the interaction between hippocampus and different neocortical regions. Yeah, and with microdrives, we just keep lowering the probes until we get into a new, fresh tissue. So we can have hundreds of units recorded simultaneously. And then we train the animals to do somewhat simple behaviors most of the time. So it's either running on a linear maze back and forth, or a T-maze where they need to alternate left and right. Or recently we started to use again a lot the cheese-board maze, which is like a circular platform with 100 holes in it, and only 3 of them are baited with water.
Okay.
And then the animal has to learn every day. So every day we change the location. So the animal has to learn the new set of locations from day to day.
Neat. Okay. Very, very interesting. And so now you said that you're using multiple different types of probes. And so how, I guess, like which probes are you using and which ones do you use them for different experiments? Do you find different benefits with some of the different probes?
Yeah, the probe selection really is governed by the region of interest. When we start an experiment, you just go on to the different companies' catalogs, you scroll through what's available, and then I have a map of the brain from the atlas, and then I see whether that probe can give me the data that I need. there is, and then the other thing is the channel count, right? Like typically these days we don't really use less than 64 channel, but these are pretty much the constraints.
Yeah, so when you're looking at the brain atlas and looking at the different brain regions, how do you decide which probe is going to be beneficial for which brain region that you're looking at? I mean, maybe you can talk about the specific areas within the hippocampus and in the cortex that you're thinking about, because I know that like brain structure and also even like neuron type that can really play into the type of probe that you want to use.
Yes, so one of the main question is always later on what type of analysis I'm planning to do. Do I need a lot of cells or do I need multiple regions at the same time? And then the next question, that if I am working with mice where everything is smaller, then I need the densest available probes typically. But if I work with rats, then I need some probes that have a longer vertical span on each end. And then, like for example, CA1, it's 100 micron both in mice and rats. I would like to have a probe that has the highest number of channels within 200 microns. So that's typically a poly 2 or poly 3 probes. And then for cortex, especially for prefrontal cortex, it's something more elongated or like goes deeper in the brain, like as it folds at the midline. So that I would look for something that, can span 400 or 500 microns. But, this is always like the pick your poison situation. Do you want high density and a lot of neurons, or do you want spatial coverage in expense of the number of simultaneously recorded single units? But that heavily depends on the final questions that we try to address. Like there is no one size fit all like advice on this, unfortunately. It's really, you need to know the final analysis that you try to do and what it's sensitive to. But to be honest, I feel that we just do, 2 animals preliminary data, kind of see what happens. Is it good enough? And if not, then tweak some of these parameters, probe choices. Try to do, instead of 2 probes, put in a 3rd probe. Like there are a couple of options on that end, yes.
Yeah. Yeah, I think the analysis, kind of having that in mind before you go into the experiment, that can definitely guide you in a certain way. And so, what type of analysis are you doing with the data that you're collecting?
Well, we always do, well, for hippocampus, the very first thing that we look at is the number of place cells, place fields, and then we characterize them. With hippocampus, we are also lucky to have really good ground truth data, so we can get a good sense of the cell type based on waveform and firing rate statistics. So, and then we can also look at circuit interactions, how certain interneuron types behave during sleep and then during behavior. We do also a lot of sleep-wake comparisons because we typically do the freely moving experiments. So, our structure is sleep, behavior, sleep. So then we can look at how memory consolidation happens after the experience during sleep, and then we compare it to the pre-sleep. And then we do a lot of LFP analysis as well. So we look at how certain oscillations entering, spiking of neurons, whether certain subtype of neurons have a phase preference of these oscillations, and how different oscillations interact with each other, and then how that influences the interregional communication as well.
Okay.
But I would say, this is also becoming so sophisticated with the advance of computational tools.
Yeah.
And you can get to the similar answer with 3 to 5 different ways.
Yeah, I think that is definitely a product of the technology that's coming out now, that's been out for a while, but just the high channel throughput and the mass amount of data that you're getting. And there's so many different mathematical analyses that you can do to pull something interesting, something biologically relevant. And so, yeah, like you said, 3 or 4 or 5 ways to get to a similar answer. And now you were saying that you guys haven't been using radians, the NeuroNexus software. What software are you guys using, I guess, as far as data acquisition and then signal processing and subsequent analysis?
So we use the Inton USB port. We have a lot of those still around. We also have a couple of OpenIFIS system, and they have their own GUI, and yeah, so pretty much I think we have like 30 something recording systems in our lab.
Wow.
So it's like all the hatch stages and all these things, and yeah, it's just unless some of those will break, we don't need to invest in new equipment. So yeah, so there's the software side and then the analysis side. So before I joined the lab, there were a couple of students and postdocs in the lab who organized the past 25 years of codes into a somewhat well-documented format that we call bus code, so like the Buzsáki lab code, and it's on the lab GitHub. And it's a really good within lab community effort, so it can set you up pretty quickly to get to a point where you have your spike times and some of the LFP events detected that you care about. So one of them is the sharp wave ripples that kind of Jury discovered. And then we know that it's important for memory consolidation. We have some GUI for brain state scoring. Like one of the PhD students had a paper with a postdoc. I don't know, it's like a few thousand lines of code, but right now I just use state scoring, and then in an hour I have the brain states, right? So in this sense, I think we are really lucky that I am really, and that but everybody in the lab now is really lucky too. So we could build on top of this organized code base. Now, talking to many people over the years, I realized that actually this is really unique and forward-looking. It also helps, just to set a certain standards within lab, so we can also share somewhat easier data with each other.
That's really important to be able to do that, especially if you guys are doing very similar projects, wanting to, I guess, have that consistency and the replication of it. So did you, and I guess other people in your lab, did you have a pretty good coding analysis background before joining the Buzsáki lab, or is this something that you have kind of learned along the way?
I think everybody comes in now. Like typically people pick this up during their undergrad these times. When you do a gap year research. Yeah. Like these days, surviving systems neuroscience without knowing MATLAB, nowadays mostly Python. It's just not, at least know how to use packages. So what's your background? Sorry. So have you done experiments or?
Yeah. So I finished my PhD from the Medical University of South Carolina. I finished that back in May. And I was doing in vivo electrophysiology in the locus coeruleus of an Alzheimer's disease rat. I was using Atlas probes. I was using a Plexon data acquisition system, and then Plexon offline sorter. And then I was doing all of the signal processing and analyses in MATLAB.
Okay. Yeah. So then so what I think our lab tried to achieve is to get to a point where you have your spike times, and then the most common features of LFP detected, somewhat standardized, and then kind of you are on your own, right? And then like now every PhD program has computational courses. Well, actually, that's not an issue anymore. So yeah, so you get some formal training typically, but on top of that is with this amount of data, hundreds of channels, tens of sessions, 5 to 10 animals, like it's terabytes of data. We typically spend 6 months to a year in a project to maximum, and then 2 years minimum analyzing that data, right? So I think our job is mostly sitting in front of a computer rather than actually collecting the data, training animals. And it goes like these phases that you collect data, you analyze it for a year, then you do some control experiments, or you realize that some of the data is not as clean, or you don't have enough number of neurons. You change the probe for a higher density. Also, over the 2 years, something new might have come out.
Mm-hmm.
Like in the field of electrophysiology these days, like it's just like the pace of engineering innovation is insane.
It is. It is.
I started my PhD about 13 years ago, and I used two 32-channel probes, and I thought I was like, this is like state of the art. Nowadays, 32-channel is just like, no, it's not enough. Most of the time, unfortunately.
Yeah. So I guess
yeah.
how would you describe the vast change that you've seen in the electrophysiology field over the past 13 years? Because yeah, like 32 channels at one time, you can get some really good data from that, but now compared to the high density channels, that's minimal.
I don't fully agree with this game because you could still have amazing results with just even 32 channels or even just a single wire,
Yep, that's
Many
true.
of the discoveries that we are looking at these days at high densities were made with a single wire or one single tetrode, right?
Mm-hmm.
So it's yet to be seen what we are going to gain with thousands of channels.
Mm-hmm.
But I think it's also something, that it's like, so now engineers, companies gave us all these tools, everything is smaller, lighter. So I think it's now our job to rephrase our questions and mindset to utilize these tools to their fullest potential.
Mm.
But I think it's hard, to be honest, like it's hard in a sense that once you move beyond the few hundred channels, you do, let's say, 2 or 3 64-channel probes or 128-channel probes, right? Then the efficiency of your coding, your programs becomes important. The data transfer takes time. That then making a silly mistake is more costly than when you run something on a 2 gigabytes of a file versus 200 gigabytes or 1 terabyte.
Mm-hmm.
So I think this is something that I personally feel that I also didn't have such a good education in computational neuroscience, but I also didn't need to pay attention for efficient coding, right?
Mm-hmm.
But these days, I think all these tiny things are important as well. But yeah, but I don't think we are ready, to be honest, for this amount of innovation. Yeah.
Yeah, I feel like what you're saying, the quality control it's got to be really interesting. And I guess before I did in vivo electrophysiology, I was doing patch clamp recordings and field recordings in Slice. And with that type of data, it's really easy to look at it and say like, something funny is going on with this one cell. Whereas, yeah, if you're looking at thousands of neurons, it's hard to tell if you've made a silly mistake and something is off.
Yes, but just to give you another example, like when we were using these synapse probes, right? It's 1,000 channel, and then the software had this nice heat map. Like, sorry, simple question: how on earth are you going to visualize 1,000 channels?
Mm-hmm.
And even if you have such a big screen, like our eyes, brain cannot make sense of that amount of data.
Mm-hmm.
So, and then one funny thing was that there was this heat map representation of spiking activity, but at that channel level, that high density channel count level, even a heat map representation was enough to know where we were in the brain.
Mm-hmm.
Right. So, but these are things that I think is just the new era where we learn as we go, and we just need to be open-minded for changes and accept that, well, this didn't play out as well as we hoped for, and then just change, I guess.
Mm-hmm.
But yeah, to be honest, I don't know.
Yeah, I think being able to pivot is a really important mindset to have doing this kind of work. And so now you said that you were using the synapse probes, and so how was your experience with those?
It was good. I think it's especially the 8-shank probe for just given our region of interest with hippocampus and cortex. I think that's the most suitable for our experiments and questions. We also planned a couple of experiments for the 4-shank design. So I think it's really a great device.
Mm-hmm.
It's just, our lab is really focusing on the role of sleep in memory consolidation.
Mm-hmm.
Because the probe is relatively bulky and the cable is short, we could only do head-fixed experiments.
Yes, that would be limiting.
So we couldn't do freely moving experiments, yes.
Mm-hmm.
So because of that, look, when you have such a great piece of technology and this amount of data, I think it's not that difficult to rephrase some of the questions that we care about. But it's just the nature of our type of experiments that we really, really look at almost in every single project, okay, so what happens after the experience during sleep, right?
Mm-hmm.
And if I don't have access to that data, then it's a bit harder to fit into the results into the bigger picture that I have been working on. But yeah, overall, so I would say that if there was a chronic probe available, it would be amazing. But in general, I really think that it's, like seeing that level of detail online, even as you just record the data, but when you start analyzing, it's just really unprecedented. There is no more questions, I would say. Like you can really see everything. It's just crazy.
Yeah. So now, and for me, just because like I'm still learning a lot, but so you have used both the Synapse probe and Neuropixels probe, and like both high
Yes,
density, high channel. How would you compare them?
pretty much the same. I mean, there are pros and cons, I would say. So the obvious big advantage of Neuropixels is available for chronic,
Mm-hmm.
but the huge disadvantage is that you only have 400 channels available.
Mm-hmm.
I don't think people truly realize that how limiting that can be if you are not recording from cortex only.
Mm-hmm.
Like for example, you might select the channel in CA1 and you have channels in CA3, but because of the bank channel selection system, you might not be able to select that channel chunk.
Mm-hmm.
So then you cannot really ask inter-regional communication question because you just cannot select it. So, and in the Synapse, it's the 1,000 channel is always available. So you get all these informations.
Mm-hmm.
So I think in this sense, it's better. But yeah, but I really feel it depends on the question, like, yeah.
Mm-hmm. Yeah. No, I totally get.
But I think I don't know if you have seen at SFM that the Neuropixels 3.0 is coming out with 1,536 channels simultaneous.
Oh, wow.
Yeah, so that's going to be yet another game changer. Yeah, so, but I think so far I would say that for some of the questions that we care about, if there was a chronic version of Synapse, it's better for our experiments than the Neuropixels.
Mm.
Yeah, but to be honest, for me, sorry for saying this, I know you are from
No,
that
it's
company,
okay.
but
Be candid. Be
it's
candid.
it's silicon probe,
Mm.
it gives us nice results, and I don't necessarily like the hype around, like, I don't even like that people don't even refer Neuropixels as a probe anymore. And I know it's not a silicon probe because it's different technology,
Mm-hmm.
but when people say that word, you say, oh, magic. It's just another probe for extracellular electrophysiology. It's a very fancy one, don't get me wrong. It's a really nice one. It's almost highest density available,
Yeah.
right? It's just a probe, right? So, and to be fair, when you use Neuropixels for CA1 pyramidal layer, that is 100 micron, you don't need Neuropixels. It's useless. You can put in more channels with a poly 3 configuration into CA1 than with a Neuropixel,
Yeah,
right?
getting back to the specificity of the region that you're recording from, that should really dictate the type of probe that you
Yeah,
use.
but Yeah, you record it from locus coeruleus, that's what you said, or after?
Yep, the locus coeruleus.
Sure. So why would you need 400 channels there? It's so small,
It is
even
so
in a
small.
rat,
Yeah.
right?
Yeah, it would be overkill. And I mean, I think that one could argue that you're getting more information about the circuit that that region sits in, and maybe you can paint a more informed story about what's going on locally there. But yeah, if you're really just interested in one region and even just like one type of neuron, covering that amount of space is kind of overkill.
But that's what I think, people don't, again, fully realize until they start planning their experiments and start doing it, that typically your regions of interest are not aligned in one insertion plane. So, even let's say you are interested in locus coeruleus, and then you want to get some of its target in cortex, then it's unlikely locus coeruleus is so posterior. Like it's unlikely that one of their main targets would be the same penetration even for a Neuropixel. So then you are way better off using two probes, but then why would you record 200 channels around the locus coeruleus that are, I don't know, a bunch of other nuclei? I don't even know what's around that, but like not necessarily related to your question.
Yeah.
And then you are just filling up hard drives with data. So, and that's to me back to the point of, sure, then 264 channel for a particular question, or a 32 and a 64, or, any of these combinations could be just so much better.
Yeah, I definitely agree. Um, and so in addition to the high channel probes that you guys are using or that you're using, are you also using like 64, 32 channel electrodes?
32, not anymore. No, 64 sometimes, especially the linear shank configuration or the polytree. Those two, and then just higher.
Okay.
Right?
Yeah.
Because also, like it's just again very simple math, right? Like the more channels you have, I mean, within a certain volume, the more neurons you get. And again, this is for me the point, that like it really doesn't matter. Neuropixels, 64, 32, 16, 128 channel. The surgery is the same effort. Training the animal is the same effort, and collecting the data is the same effort. The only thing that is changing is the number of neurons, right? And the complexity of your data analysis is really dependent on the number of neurons that you can get.
Yeah. So that's something that
So,
I'd be interested in your opinion on it. So when I started doing my experiments, I was doing it with a single channel electrode and I was getting really clean signals. And then when I upped it to 16 channels and 32 channels, I noticed that I felt like the signals were they were a little messier. And so I don't know if that was just something that I was seeing. I guess, how do you see any difference in the higher amount of channels, the intricacy, the complexity of the analysis? Because I mean, there's a lot more signal to kind of work through and parse out those individual units. In terms of data analysis, how do you find the higher?
I mean, yeah, like that's absolutely right. Like if you have 100 neurons and then you can stack them into 100-dimensional space, versus you have a single channel with two neurons and you have a 2-dimensional space, that's not the same type of questions that you can ask from the same data, right? But again, as technology advances, computational tools are advancing, and we have tools now to analyze this type of data. I would say the jury is still out there, like what is a good analyze information transfer between regions, like there are 3, 5 different methods. We don't really have the ground truth. We don't fully understand the mechanism. So the jury is still out there, which one would be kind of a gold standard. But I think in a couple of years we would get there, and then people would mostly use that method. But in general, this is where I try to refer to as well, that now we mean systems neuroscientists should change our mindset and start asking somewhat better, but also different questions that is suited to this high complexity data. But yeah, no, definitely. I mean, and also, like now we have animals with hundreds of neurons, and then when you start playing the game of downsampling, so what's the minimum number of neurons that you need for certain results to still hold? It seems that we have for hippocampal physiology, we have a magic number around 150 to 100 neurons. Below that, most of the analysis would be just too ambiguous. And yeah. So and that's what I feel that it also depends on your question, right? Like it still seems that motor cortex can still encode a motor trajectory within 20 neurons, right? But who knows if we would have 1,000 neurons there simultaneously, whether other decoders could perform 100 times better, like this is still ongoing, and I don't think we have a clear answer to this question. Going back to, I've been thinking a lot what these high channel counts data, so how did they transform neuroscience knowledge, and where do we have the new Hebb's rule, the new theories yet to be seen?
Yeah. And so when you said that as electrophysiologists need to change the questions that they're asking to best utilize the types of data that is being acquired, how do you think that people need to change their questions?
I don't know, actually.
Yeah.
The very first thing that we really need to think is how to utilize the animals and the amount of data better. Meaning that, if I have a question even with optogenetics included, is there an other interesting optogenetic stimulation paradigm that can be useful for another project? And me, personally, I might not look at it. I would say it's like in a utopistic world, it would be, like 3-4 labs or even more identify key questions and some of the experimental pipelines. And then again, for you, for us, the surgery and all this takes the longest and the most difficult. But if I know that, just very simple thing, you would be interested in, again, hippocampal neocortical communication, and then you would say that, okay, I will prolong ripples. It has been shown it helps memory consolidation. But what if someone would propose that, but what if we do, now we have a study that looked at when ripples are happening in close proximity to one another. So, and then instead of prolonging ripples, we would just create more within a short period of time. Same animal, same surgery, same number of neurons. It's the only thing that would change is the stimulation parameter.
Yeah.
Right? And then immediately you can kill 2 birds with 1 stone. But this high channel data, and with the complexity of the data, we can start thinking more than one probe, one animal, one project.
Yeah. And I guess that kind of feeds into my next question, but where do you see the field of electrophysiology going in the future, the next 5-10 years? Do you think that it's just going to be upping the amount of channels, upping the amount of probes, upping the amount of regions that are being recorded? Do you think it's just going to keep increasing? Or I guess, how do you think things are going to continue to evolve?
I think in the next 5 years, it's going to still be a number game, but unless we prove to ourselves that these numbers are needed and beneficial, I don't think it's sustainable and it really makes sense. But I also think that now people are starting to think more about when you look at some of these papers that, like it's always distributed representations across the whole brain, basically. And if it's not really feasible to record the whole brain, but can we get closer to that? And, these very high channel count probes could be, for me, what I am thinking around the lines of use those as like a fishing expedition of see which regions are important.
Yeah.
And then zoom into those regions with the knowledge of, okay, these are the important ones. And then you can switch probes and switch devices to fully utilize, let's say, again, in our case, we find that this cortical region is the most important in hippocampal neocortical communication. Then after we identify certain targets, although hippocampus is not a good idea because we already know so many about it, but some subcortical regions with certain cortical targets, and then you can do a subcortical probe in, like one probe in the subcortical region and one or two probes in the main targets, right? And then you can refine the experiments somewhat better. But yeah, so far it seems to me, given the past 5 years, that it's an increasing channel, increasing unit number of game. But I also think unless spike sorting will be solved for real, we will not get so much ahead.
Yeah, yeah. Very, very interesting. Yeah, I'm very excited to just kind of see how things continue to evolve in the sphere of specifically electrophysiology, just because it's come so far and there's been so many things going on. Awesome, cool, great. Well, I've really enjoyed this conversation and getting to chat with you and just kind of pick your brain about what you're doing, and I guess getting a little more like philosophical with things in general has been really fun. And so just to make sure that I have this correct as far as the NeuroNexus products that you're currently using in the lab, I can kind of loop Synapse in there, being a distributor for them. And what other type of probe did you say that you were using from NeuroNexus?
We have the Poly 364 channel.
Mhm.
Yes, we have a couple of them. We have the
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 five.
5-shank probe,
Okay.
where the middle shank is longer.
Okay. Okay.
I don't know what's the official name of that probe.
Do you guys, because I know that we have a Buzaki probe. Do you guys, and I'm blanking right now on what the design of that is, but is that let's see.
We like that as well. So I think the 5x12 is pretty much the same configuration.
Okay.
Yes, and then we have some of the linear probes, like 64 channel linear, 20 micron spacing, because that's also useful. But I think one of the most useful for us is still this 5-shank, where the middle shank is much longer, so that can cover the LFP across the hippocampus, and then the other 4 shanks has really high density. I think it's not Buzaki style, it's the staggered style instead of the Buzaki, but it's high density, so it's also, it's good. Yes. So I think pretty much these are the probes. Yes.
Yeah, awesome. Very cool. And then, so right now you guys aren't using the Radian software, but you guys have a license for it. I think that's what I saw.
We might have, but yeah.
If I'm thinking back to my conversations with Aussie, that I think you guys do have a license for it. And if you're ever interested in getting kind of a run through to use it, our software developers, they're great, but especially if you're using our probes, because then you can, and maybe you guys already have this, but being able to see the activity in real time across the probe is really useful, as I'm sure you know.
Issue is that for that we also need your recording device, right?
Yes. And are you guys, you said using Intan right now?
Yeah.
Okay. Yeah. Well, I know that there's been talk about, because we used to support Intan, or I guess Intan could support ours. And there's been talk about doing that again. And so maybe I'll bring that up to the team.
It's just that we buy a new recording system when we have all the other recording systems, right? And then if your software is only compatible with your recording system, which makes sense, I understand. But that means that we will never be able to use your software because we already have the recording systems, and recording system, I don't know how much yours is, but it's in the ballpark of 10 to 20K.
Yeah.
So why would we spend 20K when we already have all the tools, right? So it's,
Yep.
I mean, this sense, Jury's lab is a well-established huge lab with all the resources, right? So it's not a typical environment, I would say.
Yeah, no, I totally get that. Great. Well, thank you so much for taking the time to chat. What you're doing, it sounds really interesting. And even like your approach, it sounds like you're really thoughtful about the science that you're generating. Really, it's really nice.
Thank you. It was really nice meeting you. And hopefully we can use your products in the future as well. I would actually that for reusability. And I know it's not your company's main idea to reuse probes because it's not good for the business. But in terms of reusability, the most stable probes are always the NeuroNexus probes. I don't know why and how, but in terms of longevity and signal quality, it's the most superior that I have ever used in my life.
That's feedback from a lot of people. So I'm glad that they're working for you.
Yeah. Okay. It was really nice meeting you.
Yeah, you too. Enjoy the rest of your day, and
Thank
we'll be in
you.
touch. I'll talk to you later.
Okay. Have a nice day. Bye.
Bye.
All right, everyone, that is the end of today's episode. Thank you so much for tuning in. We've linked today's guest in the show notes, so please go check them out. They're doing truly incredible work. You'll also find a list of the NeuroNexus products they used in their research, which we hope is helpful whether you're setting up a lab or optimizing your current workflow. This show wouldn't be nearly as interesting without the researchers who join us. If you're using NeuroNexus products and want to showcase your work, we'd love to feature you through a full episode, a short spotlight, or simply sharing your research with the community. You'll find a showcase submission form link below, so go ahead and fill that out. If you found this episode interesting, make sure you're subscribed so you never miss a conversation. We're actively building connections within the electrophysiology community, so come join us on LinkedIn, X, Blue Sky, Reddit, and Instagram. This podcast is powered by NeuroNexus Technologies, advancing electrophysiology at every step. We'll see you next time.